start at past, and my plan is that even if no one is here at past, I'll start teaching and recording. All right, so you, um, then we will save a bit of time. So I'm going to try to use, oh, can I ask you, are you all confident finding documents in Google Classroom? Give me a tick if you're confident and a cross if you're not. All right, because even though the Moodle has the weekly work there, I also add like revision, I add extra comments around the weekly work. So I really want you to see the document that I put in Google Classroom. So you'll notice that I've got in my document that not everyone in the class has sent in their last SAT. Some of them it's perhaps because the school didn't send it before the holidays. I'm not quite sure why I haven't got them all yet, but as soon as I have got them all and mark them, please, part of your learning and your consolidation is to do those corrections. Now, I'm not sure if I did a slide. Yes, I did. So far in term 1, we've done further differential calculus. We're now about to start continuous random variables, and then we go to integral calculus. Integral calculus is the reverse to differential calculus. So you must be very confident with your differential calculus. Who is very confident with their diff calculus? So what you will find is we do the simpler, to begin with at least, the simpler processes. But still, that is why you must understand thoroughly the work already done, because we build on it. And I just want you to see that we begin with continuous random variables. It's just a 3-week topic, 4-week topic. And later, after integral calculus, we go back and we continue. Oh, sorry, I've written it backwards. We do the continuous after the discrete. So just a bit of an idea of where we're going. There's also a mid-year exam at the very start of term 3. That consolidation for the mid-year exam is really essential because a lot of students get a bit of a shock, especially if they haven't done many exams before. They get a bit of a shock at the time required to consolidate their learning. So in a couple of weeks' time, I'll start to say, have you got a revision program in place? And I've got another question for you guys. Have you ordered your MASA revision guide for maths methods? Excellent. I just got the science ones today for the teachers, so I'm assuming the maths ones will be coming anytime soon. So as soon as those study guides arrive, they are an excellent resource because not only do they have exams, they have very simple, straightforward questions. They also have exam standard questions and past exams and fairly detailed solutions. So I believe they are an excellent revision resource. So can you just do this? Can you write down in text chat? I'm just going to give you 2 or 3 minutes. What comes to your mind when you read the words random and continuous data? I've just noticed the recording was turned off, which is a bit of a problem with me. I keep forgetting to turn it back on. So let's do a problem. So have you got paper and pen out, and just put today's date on the top if you like, and let's just do a problem together to focus on the language and the notations. So just give me a tick when you're all ready to go. You've done it already. You're certainly organised there, Hannah. So please, can you highlight as you read? Just highlight so that I know that you're focusing on the key information. So yes, I'm glad you've read that, but also can you read the actual little exercise? So as I see the capital X highlighted, that is the variable that has to be defined, and it's been defined as the sum of the numbers. So I'm not going to follow this exactly. So X is the variable that we've defined, and little x are all the outcomes. So the outcomes would be, there's two spinners, so 1 plus 1 is the lowest sum. The outcomes would be 2, 3, etc. So now, can anyone explain why the variable x is a discrete random variable? Thank you, Hannah. All right, does anyone want to, you said it's going to be a whole number every time, so I'll just abbreviate that, whole number. Does anyone want to discuss that reason for it being a discrete random variable? All right, so the randomness is the spinner is random, so it can't be predicted, and it can be measured every time. So can you see that Hannah's, if I said on the spinner the numbers were 6.3, 1.8, so the sum would not be a whole number, but it would still be discrete. Smiley face if you can see how the careful definition that Brett has given, it can be measured every time, means that the measurements might not be whole numbers. So thank you. And Hannah, I hope everyone is happy to do what Hannah has done, put forward an answer, and we work with that answer and refine it. Explain why exit we haven't done that. Oh, well done. All done. Now, I've just asked, are we interested in anything else with these spinners? Can anyone put a story? Why should we care what the sum of the spinners is? All right. My betting comes to mind to me that not all of those outcomes have equal probability. To get a double one or a double of any numbers is less likely than getting a sum of 7, because the sum of 7 you can get with 1 and 6, 2 and 5, 3 and 4. Yes, it does, Brett. So we've got all these different probabilities, and the outcome is different for different combinations. And so if you're betting on what will appear, then you're going to bet on a 7. And maybe that's why seven's a lucky number, who knows? But the probability of a sum of 7 is higher than the probability of a sum of 2, for instance. So we see patterns, which was mentioned before, and we can we've got an expectation of what will occur and we can make decisions based on those expectations. All right, so can you again have a look at this question, highlight key information? All right, so let's assume you're ready to do part A. Do people want to start saying the possible values of x? So reread, the variable x represents the number of games played in the final series. So how many games might be played in the final series? Yes, Hannah? It's games. Are you looking at the same screen as me, Hannah? We're looking at number 4 on the screen, Hannah. Um, so have a look at what Brett has written. Brett, do you want to talk to... Brett, just be polite. Do you want to talk to your response there, please, Brett? Not really. Yeah, thank you very much, Brett. I think that was extremely well expressed. Um, so, had people begun, were people still grappling with the definition, or do you follow what Brett has done? He's, give me a tick if you follow that range of values that it must fall in. So here we've got a pretty, if you don't think like that, you're sort of stuck. So this idea of a range of possible values, what is the least number it could be? What is the maximum number it could be? That is a really good starting point in your deductive reasoning. So the values, the variable was defined as the number of games needed to win. So just like Brett has said, so that capital X and the little x is the outcome. So the outcomes, just like Brett said, is 4 games, 5 games, or 6 games, or 7 games. And you can't have 2 winners, so you can't have, potentially with 8 games, you'd have 2 teams that had won 4 games. So what I recommend is that if you read a question, you think they haven't given me enough information, talk to somebody, just try and work out. Usually they have, all right? Usually there is enough information and you've just got to say, how can I pull out a new idea from that information? All right. So for it to last exactly 5 games, yep. I hope that that's pretty straightforward. Yes, Hannah, it is confusing. So with this question and with many of the questions, getting your head around what they're talking about and exactly what it means is the skill. And once you've developed that skill, you might, Brett was very quick, so well done, Brett. But that is just a matter of practice and thinking in the right way. Oh, has someone gone ahead? Excellent, Hannah. Um, I didn't know that students could do that. So, so now I'm still focusing on the notation because I actually believe you will be able to do these exercises fairly straightforward, and I want you to think about the meaning of what's written down. So let's catch up with Hannah. The variable x is the number of heads when two coins are tossed. So the outcomes, the little x, is you could have 0 heads tossed. You could have 1 head tossed. You could have 2 head tossed. So there are only 3 outcomes and they're countable. So it's a discrete random variable. Now, we're going to look at the capital probability P that the variable we're examining, capital X, equals the outcome, little x. So the outcome of 0 heads, the probability is a quarter. Can I have a light bulb? Do you say, oh yes, I can read that and I can understand it? What I'd like you to do, I haven't actually asked you to write very much, but I'd like you to write on your own bit of paper probability distribution and just do the notation. The probability when the variable x has the outcome of 1 head, can you just write that notation down and write down the probability? And just give me a tick when you've done. And as you're working, I want to tell you that when I look at your weekly work, I'm going to be looking for the notation. Because if you just write equals a quarter or equals a half, without the subject, the probability that variable x equals 1 equals a half, it is incorrect. So you must write down the symbols correctly. See you, Brett. Yes, Hannah? I haven't looked. Are you telling me, Hannah, that they just have the answers in the back of the book? Yeah, I I am not impressed sometimes. Look, I understand that they've condensed the answers down to minimum space. So please take on board that you in your presentation must show I call it a sentence, but it's the mathematical notation correctly. Okay, so let's go on now. I didn't see ticks from everyone, but let's go on. If we can you please connect the table of outcomes and their probabilities with the probability distribution? So it's called a column graph. Is there anything you notice about the distribution? Yes, Hannah? Yes. So not skewed. Um, so it's symmetrical. Any other things that people notice? Does it, is it, in your opinion, can you get the information more easily from the table or from the column graph? Yes, Hannah? Yep. Can you, what makes the graph helpful visually? What's helpful? Well, following what Hannah's already said, she said that she's noticed that it's symmetrical. And I think the distribution or the shape of the data, so the distribution of the data, especially if we had, 10 outcomes, is much more easily seen visually with a column graph. Hannah has also done, even though this is discrete data, she's actually drawn a shape. And actually, probably not till later in the year, we're going to see that discrete data can be approximated to a normal distribution. So a normal distribution is on usually a description of continuous data, but you can approximate. And normal distributions can have a formula, and therefore the prediction is helpful. And now I'm just going to go ahead a little bit, because when we do integral calculus is going to show you that the area under a function um, can be calculated, and the area under this probability function would be 100% of outcomes. So that would be the number 1. So I'm just trying to point out that there's going to be a link between our integral calculus and our statistical analysis. And when we're looking at data, we are really interested in the distribution. So if I just go to the whiteboard for a second, and if you were a team manager and you were picking a team of players and you looked at the distribution of how they throw goals, and one player, oops, that's the wrong thing. One player I've done it symmetrical, but I don't have to. And the other player, so if the area under both those graphs was equal, so they've, in their season, they threw exactly the same number of goals. So the area underneath both of those is supposed to be equal. Which player, I was meant to change colour, but it didn't work. If this is player 2 with the peak, and this is player 1, which player would you choose as a goal thrower? Yes, Hannah? Yes, it is. Same amount of time, same amount of goals, but the distribution of the way they throw the goals is different. Yes, so you're saying that either of them would be fine. Any other opinions? One other, you might want consistency. So if as a coach you wanted someone that nearly every single game threw some goals, you might choose player number 2. Because even though they didn't get a fantastic score, they didn't have terrible ones either. So if you were looking for consistency, then you might choose player 2. If you are just saying, it depends what team they came against, all sorts of things, that overall they've got the same number of goals, one wasn't more consistent because this is a low number, the left is a low number of goals and the right is a high number of goals. So some matches they didn't get hardly any and others. Okay, so this is off the top of my head, but it's trying to show that depending on what you want, that the way the data is distributed becomes very important. And so that's what we'll get to eventually. Now, earlier on in this lesson, we talked about uh, defining discrete random data, and noticed that it added up to 1. All the outcomes probabilities added up to 1, and all the probabilities were within 0 and 1. So if you just have a look, dot point 1 is saying to be a valid probability distribution, the probabilities P little I represents all the different outcomes. So in that coin toss, the 2 coins and the variable X being the number of heads, there were only 3 outcomes. So I, in this case, will be 1 to 3 to represent each of the outcomes. The other thing was that summing up all the separate probabilities, so here's the separate probabilities, we're summing from 1 to n, the total probability is 1. And the last dot point is set notation. So the curly brackets is the set of probabilities for the outcomes, 1 up to the nth outcome. That's really just a definition. It describes a probability distribution. So can I have a tick? Is all of that notation similar? People used to using the sigma for sum. Are people comfortable, or is it new? Tick if you're comfortable with it. Cross if it's new. Yeah. Okay, thank you. So a lot of this learning, yes, that's right. You are all meant to have done some last year. So when you, in the weekly work, I set chapter 6 is totally revision. Just read chapter 6, read the notation, remind yourself of things last year. What you'll find is chapter 7 is a bit of a summary and a repeat of chapter 6. So read chapter 6 pretty quick unless you don't know it. So we've concentrated just on chapter 7 with the assumption that you know chapter 6. So with those points, really it's the first 2 points mainly for a probability distribution. Do you agree that this example is a valid probability distribution? Does the individual probabilities fall between 0 and 1? Is the sum of probabilities equal to 1? So just give me a tick if you say it's, just write valid in text chat or not valid. Can't. Well, just take your time, add it up, get out your calculator and add it up. Because see, this is using the chart. You're going to add up these probabilities on a calculator, see if it comes to 1. Yeah, confidently valid. Now, see, both Reese, no, they can't, Hannah. You've got to be confident. So, Reese, is that a style of speaking? Are you absolutely confident that it is valid? So, that's going to be important. Thank you. Thank you, Reese. So, in your thinking, it is actually important to have clarity of thinking and expression because part of this is confidence. It definitely adds up to one. Um, the individual probabilities are between 0 and 1, um, and it is a discrete distribution. Now, something I hope is a bit of a recap. If you were asked for the mean is the average. So if you multiplied, I haven't given you the chance to read this question. So it's about customers in a magazine store. How many magazines do they buy? And so the number of magazines bought is the variable. So, and the outcomes are they buy 1, 2, up to 5 magazines. Apparently, this store's pretty lucky. No one comes in browsing. So one of the outcomes you might expect was 0, but um, for this shop, it's not. They all buy magazines. So to work out what they buy on average, you'd need to multiply the outcome of, let's say, one magazine by the probability. So 1 times 0.23, and and if you added it to 2 times 3.8, because you can see that just by looking at the numbers or by looking at the table, that quite a number buy 2 magazines. So you're going to expect the mean probably to be 2. So the mode is the most frequent. So the most frequent is 2. The mean is the average, and I've just quickly demonstrated that the mean, which we can use mu, is equal to adding up the outcome number times by the probability and then dividing it by the number of outcomes to get the average. And then um, the median is the position that is in the middle. So hopefully that's just a bit of revision. And I was going to do expected values if I could get there. So expected values will be next week. Which symbol? Oh, the mean symbol is Greek letter mu. All right, population mean is a mu, and sample mean is x bar. Is that familiar, people? Yeah, should be familiar, but it's not. Yes, okay. So that is, I suspect, if you're already up to date with all your other maths and you've already marked and corrected your test, then the actual work this week is fairly light. But on the other hand, if you take time to practice the symbols and get your definition meanings, like it is really important because when we go a bit faster with the actual statistics, the assumption is that you can quickly interpret the notations. And this, you'll get a SAT. It's already May. It's the next SAT is in June. So you must keep up. Um, any questions or comments before we end the lesson?